Current carrying semicircular wire or coil. Current carrying semicircular wire or coil, and force experienced by the semicircular wire in a transverse magnetic field. Current carrying semicircular wire or ring in a transverse magnetic field. In a transverse magnetic field, and force experienced by that current carrying semicircular wire or ring. Force acting on the semicircular wire. Current carrying semicircular wire or ring in a transverse magnetic field, and force acting on the semicircular wire. This is a semicircular wire or ring carrying a current I. This is a semicircular wire or ring carrying a current I. Now we can denote the axis of this semicircular ring or wire. This is the axis of the semicircular wire. Imaginary axis of this semicircular wire. An electric current I flows through this semicircular ring or coil. I is the electric current which is flowing through the semicircular ring or wire. Here I is the current which is flowing through this semicircular wire, and on this semicircular wire, or this semicircular wire is placed in a magnetic field which acts outwards. So you are denoting the transverse magnetic field by dot sign. That means this magnetic field induction or magnetic flux density acts outwards with respect to the plane of the semicircular wire. This is the magnetic field induction acting outwards, and we can denote this direction or horizontal direction connecting the two ends of this semicircular wire, and this will be the x-axis or horizontal direction connecting the two ends of the semicircular wire or ring. And also we can denote vertical axis y, and a point P. We can denote also a point P, and connecting the point P on the semicircular wire from the center O of the ring. Center O of the ring. The angle subtended by the straight line OP with the vertical axis or y-axis y is theta. Now we can denote a small element at the point P of length dl, and that small element of length dl makes an angle d theta at the center O of the semicircular ring. This is the small element at the point P. Here dl is the length of the small element on the semicircular ring. dl is the length of the small element of the semicircular ring at the point P, and this small element of length dl makes an angle d theta at the center O of the ring. D theta is the angle subtended by the small element of length dl, and in this case R is the radius of the semicircular ring. Here we can denote the average radius. R is the average radius of the semicircular ring. That means R is the distance of the imaginary axis from the center O. Along the tangent PT, electric current I is flowing, at the point P on the semicircular ring, and we can denote the direction of magnetic flux density at the point P on the semicircular ring. So this is the direction along which this is the direction along which magnetic flux density, that means vector B acts, uh, that means vector B acts outwards, and the direction OZ, the direction PZ is perpendicular to the plane of the semicircular ring. Also, we know that the force vector F equal I vector dl cross vector R. I vector dl cross vector R. And from this equation, we can find the expression of force experienced by the small element of length dl at the point P on the semicircular ring. According to Fleming's left hand rule, according to Fleming's left hand rule, the force experienced by the small element of length dl at the point P of the semicircular ring will be acting along the direction OC, that means radially outwards. According to Fleming's left hand rule, the force experienced by the small element of length dl, that is df, acts along OZ. That means this force acts radially outwards with respect to the semicircular ring, or with respect to the current carrying semicircular wire. Also, we can consider another small element at the point Q. This is the imaginary radius with respect to the point Q on the semicircular arc, and we can consider a small element at the point Q, small element of the semicircular wire at the point Q, and which makes the angle d theta at the center O. This is the small element of length dl on the semicircular wire. dl is this is the small length, or dl is the length of the small element at the point Q. Now the small element of length dl will experience a force df which acts along the direction OC prime, along the direction OC prime. So here we can denote the direction, that is OC prime is the direction along which the force df experienced by the small element of length dl acts. Similarly, the small element at the point P will experience a force df along the direction OC. And this small element of length dl at the point Q experiences a force df along the direction OC prime, along the direction OC prime. Now, the force df along the direction OC makes an angle theta, with the y-axis or with the vertical axis. Similarly, the force df along OC prime makes an angle theta with the vertical direction. Now, this force df along OC can be resolved into two rectangular components, At the two ends of the semicircular wire or ring, the angle is theta equal pi by 2, and at the other angle theta is equal to minus pi by 2. The component of the force df along vertical direction is df cos theta. The component of df in vertical direction is df cos theta. Now, df is the force experienced by the small element of length dl at the point P, is resolved into two rectangular components. One of the rectangular component in vertical direction is of df in vertical direction is df cos theta. The component of df in vertical direction is df cos theta. The component of df in horizontal direction will be df sin theta. That means the other component of df in horizontal direction is df sin theta. df sin theta is the other rectangular component of df. or the force experienced by the small element of length dl at the point P. Similarly, the force df along OC prime can be resolved into the rectangular component df cos theta in vertical direction, and in horizontal direction the component of this force df will be df sin theta. Now df sin theta and df sin theta will cancel out each other's effect, and net resultant force will be and a df. This force df experienced by the small element at the point q is acting along OC prime, and df is resolved into two rectangular components df cos theta and df sin theta. Df cos theta is in vertical direction and df sin theta is in horizontal direction. Let dl be the length of small element. dl be the length of small element on the semicircular current carrying wire. dl be the length of the semicircular wire at the point P. dl be the length of the small element of a current carrying semicircular wire or coil. Current carrying semicircular wire carrying a current I at the point P. In the diagram, this is the small element. This is the small element of length dl. dl is the length of the small element at the point P on the semicircular wire carrying a current I. This small element at the point P makes an angle d theta at the center O of the semicircular wire or loop. The small element at the point P makes an angle d theta at the center of the semicircular wire. This is the semicircular wire in the diagram. O is the center of this semicircular wire, and this is the small element of length dl at the point P. And this small element makes an angle d theta. D theta is the angle subtended by the small element dl on the semicircular wire at the center O. And the current element I vector dl acts along this tangent pt, and magnetic field acts outwards. That means vector b is the magnetic flux density which acts outwards or perpendicular to the plane of the semicircular wire as shown in the figure. This small element dl at the point P experiences a force df along OC. The force experienced by the small element of length dl at the point P in this transverse magnetic field will be df, which acts along OC. The force experienced by the small element of length dl at the point P of the semicircular wire in the transverse magnetic field B, and this magnetic field B acts outwards, is given by vector df equal I vector dl cross vector B. Therefore df, that means the magnitude of the force, is I dl B sin 90 degree, because the magnetic field or magnetic flux density is perpendicular to the length of the semicircular wire. Therefore df is equal to I dl B. df is equal to I dl B, where dl is the length of the small element and B is the magnetic flux density or magnetic field induction at the point P, such that magnetic field induction is acting outwards. So we get the expression of force experienced by the small element, that is df is equal to I dl B, and this force acts along This force acts along the direction PC, that is along OC, that is along OC. And according to Fleming's left hand rule, vector B means magnetic flux density acts outwards at the point P, and current element I vector dl acts along this direction, and force experienced by this small element will be acting along PC, and angle between I vector dl and vector B is 90 degree, because vector B acts perpendicular to the plane of the semicircular wire. So we get df as I dlb, and here we know that angle subtended by the small element d theta is equal to dl by r, length of arc divided by radius. So therefore df equal to ir d theta b. In this case, angle subtended by the small element d theta is equal to dl by r. That's why you have written df as equal ir d theta b. Therefore, we can write df as equal ibr d theta. df as equal, numerically equal to ibr d theta, which is the force experienced by the small element on the semicircular wire at the point P. Therefore, df is equal to ibr d theta. df is equal to ibr d theta, which is the force experienced by the small element of length dl at the point P on the semicircular wire carrying a current I placed in the transverse magnetic field B. df is equal to ibr d theta, which is the force experienced by the small element of length dl of the semicircular wire. df is equal to ibr d theta, and this is the force experienced by the small element of length dl of the semicircular wire in the transverse magnetic field B. And this force df acts radially outwards. This force acts radially outwards, that is along the direction PC or along the direction OC. Along the direction OC or PC. Now the small element at the point P. This is the small element at the point P on the semicircular wire, and this small element experiences a force df along the direction PC. Similarly, the force experienced by, or the force on the small element at the point Q on the semicircular wire. Similarly, the force on the small element of length dl at the point Q of the semicircular wire or coil, semicircular wire carrying a current I, in the transverse magnetic field, B, is given by, and this magnetic field B acts outwards, is given by df equal vector df equal I vector dl cross I vector B. Therefore, df is equal to ibr d theta. df is equal to ibr d theta, that is the force experienced by the small element of length dl at the point Q on the semicircular wire. df is equal to ibr d theta, which is the force experienced by the small element at the point Q on the semicircular wire, which acts along the direction QC prime, that is along OC prime, Now I vector dl of the small element at the point Q acts along this direction, I vector dl. Magnetic flux density or magnetic field induction vector B acts outwards at the point Q on the semicircular wire, and the small element experiences a force df along the direction QC prime. The force dF along the direction OC is resolved into two rectangular components, that is dF cos theta in vertically downward direction and dF sin theta in horizontal direction towards left. Also, the force dF along OC prime is resolved into two rectangular components, dF cos theta and dF sin theta in vertically downward direction and in horizontal direction. So now df cos theta and df sin theta and df sin theta will cancel out each other's effect, but the net force or the resultant force, net force or resultant force experienced by the current carrying semicircular wire is given by F equal integration df cos theta. F is equal integration df cos theta, where theta starts from minus pi by 2 to plus pi by 2. In the diagram, the two elements of length dl at the point P and Q will experience forces df cos theta and df cos theta. That means due to two small elements or the two small elements experiences the total force F as df cos theta plus df cos theta, means total force is 2 df cos theta, which is experienced by the two small elements. Similarly, due to n number of small elements, that means n number of small elements will experience total force F, which is equal to df cos theta plus df cos theta plus df cos theta plus dot 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 dot, that is equal to integration df cos theta, means F is equal to integration df cos theta is equal to integration theta equal minus pi by 2 to plus pi by 2 IRB d theta cos theta is equal to IRB integration cos theta d theta. Theta is equal minus pi by 2 to theta is equal plus pi by 2 or comma IRB under bracket sin theta bracket close minus pi by 2 to plus pi by 2, because integration cos theta d theta is sin theta only. Therefore, F is equal to IRB under bracket sin pi by 2 minus sin under bracket minus pi by 2, or comma F is equal to IRB sin pi by 2 plus sin pi by 2, or comma F is equal to IRB under bracket 1 plus 1 bracket closed. Therefore, F is equal to I under bracket 2R bracket close into B. That is F equal to I into 2R into B. So we get the expression of force experienced by the current carrying semicircular wire in a transverse magnetic field, which is F equal to I into 2R into B, where R is the radius of the semicircular wire. F is equal I to R B, I into 2R into B, which is the force experienced by the semicircular wire carrying a current I placed in a transverse magnetic field of flux density B, such that this flux density B or magnetic field induction B acts perpendicular to the plane of the wire, and where R is the radius of the semicircular loop or wire. F is equal to I into 2R into B, which is the force experienced by the semicircular wire. R is the average radius of the semicircular wire. And this is the direction along which I vector dl acts, and magnetic field induction, that means magnetic flux density vector B, acts perpendicular to the plane of the semicircular wire, that means magnetic field induction vector B acts outwards. The angle subtended by magnetic flux density vector B with the current element I vector dl is 90 degree. Is 90 degree because magnetic flux density vector B acts perpendicular to the plane of the semicircular wire, and I vector dl acts along the tangent which is in the same plane of the semicircular wire, and the force experienced by the semicircular wire is F, which is equal to I into 2R into B, and this force acts radially inwards in the same plane of the semicircular wire. This force experienced by the semicircular wire is F, which is equal to I into 2RB, and this force acts radially inwards with respect to the semicircular wire. That means this force acts radially inwards with respect to the semicircular wire. F is equal to I into 2R into B, and this force acts radially inwards, which is equal to I into 2R into B. And this force acts in the same plane of the semicircular wire, and it acts radially inwards with respect to the semicircular wire. This is a radially inward direction, and along this direction force is F, which is equal to I into 2R into B.